Okay, so in our last video, we made our first attempt at estimating the ground state energy of helium using the variational method. And what we did was to consider a trial wave function that's basically the same wave function that we would have if the electrons didn't interact with each other. And so that was mathematically given by the product psi1, 0, 0, z equals 2 of R1, that's the wave function for the first electron, times the wave function for the second electron, psi1, 0, 0, z equals 2 of R2. So exactly the same wave function for both, and we're just taking the wave function that it would be if the two electrons couldn't see each other at all. Okay, so let me actually draw a picture of that. So let's do that down here. So we have our helium nucleus, and so what we're saying is that if we only had one electron, then there'd be this kind of spherically symmetric wave function. This is like the 1s state of hydrogen, and then we're saying, okay, now there's a second electron on top of that, and we're just saying that we're going to assume that that has exactly the same wave function. Okay. So in this video, we're going to consider a different variational ansatz, a different trial wave function that is more general. So it's going to include a parameter, and it's going to take into account some physics. And so the physics is, what we're going to do is think about when we bring that second electron in. So let's suppose that the first electron is actually in this trial wave function. And so let's imagine we bring in the second electron, and we can think about, well, how much charge does that see from the remaining helium nucleus and first electron? And so if you think about it, if the second electron is very far away, then basically it just sees a charge of +1. So there's the +2 charge of the nucleus. There's a -1 charge from the electron. It's in this spherically symmetric wave function around that nucleus. And so if you're very far away from that, then you basically just see some point charge of +1. And so that's what we would have if we brought the electron very, very close to the nucleus. Then the first electron is going to be further away. It's going to be like a shell of charge, or various shells of charge at larger radii. And actually, one of the things that you might have learned in electromagnetism is that if you are inside a spherically symmetric shell of charge, then you don't feel any forces at all from that charge. Okay. And so if we thought about the second electron coming in, assuming that we're just assuming the first electron is in some fixed wave function configuration. If we brought the second electron in very close to the nucleus, then because that first electron, we can kind of model it as a spherically symmetric charge distribution. At least that would be, if you thought about the wave function classically, it's not going to feel that first electron. Okay, so what the second electron would see would just be the point charge of +2 when it gets very close to the nucleus. And so we could make a plot. So this would be R2, and the y-axis is going to be the effective charge seen by electron 2. Okay, and so what we just understood is that if you're electron 2 and you're very far away from the helium nucleus with electron 1 around it, then you're basically just seeing a charge of +1. Whereas if you come very close to that nucleus, then you no longer feel the effects of this spherically symmetric charge distribution that corresponds to electron 1. And so you would effectively see a charge of +2. Okay. Now I should say that it's a little, we're kind of mixing up the wave function with the sort of a classical charge distribution, but really here we're just trying to develop intuition. So the point is basically that when we chose our previous ansatz for the trial wave function, we were just saying that each electron is in the wave function that it would be if it were around a charge of +2. What we've just understood is that the charge actually seen by one of the electrons, that effectively depends on how far away it is. And so it could be anywhere between +1 and +2. Okay. Now all of that is just to motivate our next trial wave function. And so the next trial wave function, instead of taking the product of hydrogen-like wave functions for z equals 2, what we can do is actually leave z to be a parameter. So this is going to be trial wave function number 2. And what we're going to do is just erase this 2. Okay, so we are still going to take the wave function to be a product of 2 wave functions that look like ground state wave functions of hydrogen, but we're going to leave the z parameter, which corresponds to the charge of the nucleus. We're going to leave that arbitrary. Okay, and so basically what that means is instead of saying that our wave function for the full system is just the helium plus ion wave function for one electron and the helium plus ion wave function for the other electron, we're saying that, well, probably in the actual helium atom, the electrons are not going to be quite as close to the nucleus because of the presence of that other electron. Okay, and in physics language, we say that the first electron screens the charge of the nucleus a little bit. And so what we're doing here is allowing these spherically symmetric wave functions to be slightly more spread out. So we're probably going to end up finding an ideal value of z, which is less than 2. And we expect it to be somewhere greater than 1 and less than 2. Okay. So from the point of view of the variational method, you could just really forget all about all of that. You're just allowed to try any wave function you want. And this is a wave function that is completely allowed. So we're going to just try this wave function, use our variational method, and see what upper bound we get. And we know we're going to improve on the previous bound because our previous guess was actually just a special case of this guess when z is equal to 2. Okay, so what do? We want to first normalize, and again, that's guaranteed as long as we keep this normalization factor up here. So that's going to work. And now we just go to the next step, which is to calculate the expectation value of the Hamiltonian for our new state. Okay. And so we have that E0 is less than or equal to, and so I'm going to call this psi z. Z is our parameter. So E0 is less than or equal to psi z, and then H1, I'll call that H1z equals 2 plus H1, H2 z equals 2 plus VEE psi z. Okay. And now actually what I want to do is make the calculation look as much as possible like the previous calculation. Okay. And so remember the previous calculation used the fact that our trial state was an eigenstate of H1 and H2. Okay, so now our trial state is no longer an eigenstate of H1 and H2 because our trial state has some arbitrary Z and our H1 and H2, they're the actual Hamiltonians for helium, so they have Z equals 2. Okay, but we can just use a trick, sort of a mathematical trick. And what I'm going to do is rewrite this as the Hamiltonian H1 Z. So this is the Hamiltonian where Z matches the value of our wave function. And then I'm just going to subtract that off and add the thing we actually have. Okay, so this is just a mathematical trick, writing H1Z equals 2 as that same thing plus H1Z minus H1Z. Okay, and I'll say in a minute, it'll be clear in a minute why we're doing that. But let me just write down the same thing, H2Z, and then minus H2Z, and then plus H2Z equals 2, and then plus VEE, and then psi Z. Okay. Okay, so now I'm going to rearrange all of this. So we have this first term, and that's going to be easy to calculate because our state psi Z is an eigenstate of H1Z. And the next term is also easy to calculate because our eigenstate psi Z is an eigenstate of H2Z. And then what we have left is this big combination of things. So let's write that out. H1 Z equals 2 minus H1Z plus H2 Z equals 2 minus H2Z plus VEE. And then we have our state. Okay, so let's do these first two terms first because they're easy. Okay, so this one, so H1Z acting on psi Z is going to give minus 13.6 electron volts times Z squared. And similarly, H2Z acting on psi Z is minus 13.6 electron volts times Z squared. Okay, and so finally, let's look at the last term. And so the useful thing about this trick is that in this last term, we have H1Z equals 2 minus H1Z. Okay, and so let's have a look at H1. Okay, so that's H1 Z equals 2. That's our actual Hamiltonian for the first electron in helium. If we want to know what H1Z is, all that affects is the Coulomb potential term. So that's just the same thing with a different charge in the Coulomb potential term. And so the nice thing here is that when we take the difference, then the momentum term, it cancels out between the two Hamiltonians. And so that difference of Hamiltonians, actually, it's just the difference of the two potentials. And so that's just some function of R. Okay, so let's write that down. So this difference, I'll write it out explicitly. Okay, so H1Z equals 2 minus H1Z is just going to be minus 2 e squared over 4 pi epsilon naught R1, and then plus Z e squared over 4 pi epsilon naught R1. Okay, and then there's a similar term. I'm not going to write all this out. So there's a similar term for H2 that depends on R2. And then we've got our VEE term that was the same as last time. Okay, and so the important thing here is that we've just got an expectation value of an operator that only depends on the various positions. And so to calculate that, we're just going to do another big integral. So this guy turns into the integral d cubed r1, d cubed r2, and then we have our psi z of r1, r2 squared, and then we just have this big function of r1 and r2, and we have to do the integral. And again, I'm not going to do the integral in this video, and I'll refer you to the details in Griffiths. Okay, but I'm going to write down the answer. So the answer is the following. So it turns out to be 13.6 electron volts, okay, times 2 times, minus 2z squared, and then minus 27 over 4 z, oh, I'm sorry. Yeah, sorry, it's actually this. So the reason is that, so why is there a plus 2z squared? It looks like from the previous line, there's a minus 2z squared. But the reason here is that in the second term, there are actually contributions that cancel those first ones and actually reverse the sign. So if you take the sum of all of the contributions from all of these terms, you actually end up getting 13.6 electron volts times a plus 2z squared, and then a minus 27 over 4z. Okay, and so what we've learned is that the ground state energy for helium, it has to be less than or equal to that function of z for any value of z. Okay, so we've kind of tried an infinite number of trial wave functions all at once. And so now what we can do is our final step, which is to say that our best upper bound, or sort of lowest upper bound, is going to be what we get by minimizing this function of z. Okay. So, okay, and so that's actually a straightforward minimization because it's just a parabola. Okay, so we can use our calculus method, take the derivative, set it equal to 0, solve for z, plug it back in, and what you find is that when you solve for z, you find z equals 1.69. Okay, so that's what we expected. We expected to get something between z equals 1 and z equals 2. And then when we plug it back in, we find that our upper bound is, so we have E0 less than or equal to psi z, H psi z, and that turns out to be minus 77.5 electron volts. Okay. So that's definitely lower than our last one. Last one, when we just had z equals 2, we had minus 75 electron volts. This is minus 77.5 electron volts. And if we want to improve on that further, so we could try something even more general. Okay, and I'll just mention this because it's something that I worked out last year and I thought it was pretty interesting. So I was thinking, well, what would be an improvement on that wave function? So I thought, well, why don't we make, like here so far we've been assuming that the two z's are the same for the two electrons. Why don't we try something where the two z's could be different? Okay, so that's now even another parameter. So we can just go through the same thing, psi of R1 and R2. And so the idea here is that, well, we could try psi of Z1 of R1 times psi of Z2 of R2. That's not totally satisfying because it's not symmetric between the two electrons. And so you can add a term to make it symmetric. So psi Z2 of R1, psi Z1 of R2. And now at this point, it's not necessarily normalized, so I'm going to multiply by some normalization factor. Okay. And so if you do all of that, so that's trial wave function number 3. So now this has two different parameters that we can play with, Z1 and Z2. N is going to be fixed by the normalization. And so again, this is going to be an improvement on the last one because it just generalizes the last one. And in this case, it's pretty nasty to actually evaluate all the integrals, but it turns out that you can do it, and it ends up giving you minus 78.218 electron volts. Okay, and so finally you might be wondering, well, what is the real answer? How close are we getting? So we had a 0 parameter guess that gave us minus 75 electron volts. We had a 1 parameter guess that gave us minus 77.5 electron volts. And then we had this 2 parameter guess that gave us minus 78.218. And so our improvements are getting smaller and smaller, and we might think we're getting relatively close. Okay, and so it turns out the experimental answer is, so the actual answer for the ground state energy of helium, which is, how much energy does it take to split up that helium atom into its 2 electrons and the proton? And that turns out to be minus 78.95 electron volts. Okay, so we're actually pretty close. We're just off by 0.7 electron volts. If you want, it's possible to continue improving the variational method by just including more and more parameters, and this is what a lot of there are software programs used by chemists, especially all the time, that do this numerically, so you don't have to sit there and analytically calculate integrals. And you can get, using these methods, very accurate answers for the energies of like the ground state of various atoms and molecules. Okay,